So I hope we took a break enough. So let me start the second part. Probably by keeping this pace, probably I can finish this Hubble constant, and then I have time to talk about our telescope. Yes, so okay. So the next topic, let me switch to the next topic. So I have, you have a time, I can talk about these guys too, but then this time let me focus on this, because this is a kind of a new result from our research group recently. So cosmic expansion. I think many people know, but then let me explain this briefly. So Hubble constant is, if you look at the unit of this, then that's kilometer per second velocity, right? Per given distance to the universe. Say for given distance in the universe, how fast the universe is expanding, okay? So this is representing the expansion speed of the universe again. So therefore, this we really want to measure accurately in astronomy. Again, because this tell you the approximate size of the universe or age of the universe. Very important. But people recently saying that there is a tension between different methods. So you can imagine, right? Say, because this is a very important quantity, there are multiple ways to measure Hubble constants. Okay? Am I okay? Okay. There are two major methods here, red and blue. Red is local distance radar. So this is radar. So I'm not sure if you learned this one from Tomo-san class. I'm not sure. This means, so you combine this distance measurements. The most say reliable or fundamental one is parallax. So depending on distance to the object in the universe, the annual parallax is different, right? Because viewing, angle to see the same object changes on sky. Because our Earth is rotating around the sun, the position of our Earth changes, right? So then from different point of view, so then angle to the same source is different, okay? And parallax, people call it parallax. And then using parallax, you can measure the distance to nearby source in the universe, right? But there is a limitation, so we cannot measure distant objects using parallax. So therefore, you need to combine different methods to measure distance. This is distance radar. And the most famous one in cosmology is type 1a supernova. I'm so sorry, I didn't include the slide to explain type 1 supernova. Then maybe I don't really explain, but using type 1 supernova, this is another Nobel Prize in astronomy, in physics. And they can constrain the distance and also Hubble constant, okay? So this is the expansion speed, right? So therefore, you need to measure the distance in the universe. And also at a certain given distance, how fast it is expanding, right? So to measure this Hubble constant, you need to have measurement, the distance. So you know this, this is very simplified. So distance, you have distance here, right? And velocity. So you need two independent measurements to measure Hubble constant. Then then velocity is kind of easy, because velocity is say measured from, say, what's that? Redshift. Okay, redshift gives you the approximately the redshift as the velocity, and the only matter is distance. If you have a good method to measure distance, that can be used for cosmology. That's very simple, because usually this part is given from redshift. Redshift is easy to measure, but distance is not really easy to measure. But if you find a distance indicator in the universe, you can do cosmology. Okay. And then type 1 supernova gives you luminosity distance because type 1 supernova is the peak of the light curve is supposed to be universal. Let's say they have a universal luminosity. So then if you know the intrinsic universal luminosity, then by comparing the intrinsic luminosity and the apparent luminosity, you can measure distance. So therefore, let's say type 1 supernova gives you the distance measure. Then you can measure Hubble constant. I hope you can imagine that. That is one of the major methods to measure Hubble constant. Another is CMB. CMB is cosmic microwave background. This gives you the power spectrum of the CMB. Then people can also measure the shape of the power spectrum depends on cosmological parameters. So then by fitting cosmological models to the power spectrum of CMB, people also can constrain the Hubble constants. And then they are different approaches, okay, independent. Then usually this local distance radar is called direct method. Because they don't, in principle, they don't assume any cosmological assumption. They just simply measure distance and the velocity and then directly measuring the how fast is the universe expanding. No, basically, there's no model here. So direct measurement. CMB is kind of model dependent because to fit, so they need to fit the model to the power spectrum of CMB. The model is widely accepted lambda CDM model, right? Lambda CDM model. So that is great, right? I mean, there's a huge success of using lambda CDM to reproduce the cosmic structure in the universe, right? So basically, many people accept that lambda CDM assumption is fine within certain accuracy. That's very success. So therefore, basically, we believe that the lambda CDM cosmology is good. But anyway, in CMB, so they need to assume this lambda CDM model to describe the behavior of the universe. Then fit this model to the CMB power spectrum to constrain Hubble constant. So that means this is a kind of assuming model. So then problem is there's a statistically significant deviation between these two. At the beginning it was okay, long time ago, because they have a very large error bar. So that was, everything was happy. So then there was no problem. So there are two independent methods or consistent, I mean overlapping within error bar, that's fine. But as time goes by, then okay, data quality is always getting improved, right? So for type 1 supernova and then CMB, they always use better data, more sample, better data, high resolution, something like that. And then the error bar shrinks. And then in principle, this is good. You get more accurate measurements. But then somehow the problem starts to appear here. So somehow using different methods, now their error bars are not touching anymore. Then this difference is statistically significant because if you measure this how many sigma, so this is roughly 3 to 4 sigma tension between different methods. Now this is a very simple question. What is Hubble constant? What is the expansion speed of the universe? Even for such a simple question, fundamental question, we don't know the answer yet. So this is a problem. And then this is not just for difference between different methods, right? This may have a very fundamental question here because this is a direct method. This is assuming lambda CDM. What's wrong? One possibility is, I don't know which is the case. One possibility is, there may be systematic error in either these two, either this or this one, or both. There may be unknown systematic error. We don't know what's the error, but then there may be systematic error, right? So that's why we get wrong here. Or another possibility is, so this is assuming lambda CDM. So this assumption may not be okay. May not be, but maybe okay. So that's why this Hubble tension is very important, because this may change our assumption to describe the whole universe in future. I don't know, but this is important, right? So that's why now very important to address this issue. Then how to address? I don't know yet, to be honest. But the one thing that we can do is we can add more independent method to, or independent measurement of Hubble constant. Then let's put all of the results from different independent measurements and then to see how they are different. Then there might be a hint to resolve this issue there. So therefore, adding independent methods to measure Hubble constant is very important. So many people are trying to do so. Then, I'm saying here, right? Then, it comes to FRB. FRB may be useful to measure Hubble constant independent of CMB and local distance radar. So this is independent from them. Okay. Then how it works? Let me explain. But I already told you, actually. So now this is a simplified situation. Let's say FRB is happening here. I forgot online people. Maybe it's better to use this laser pointer. FRB is happening here. And our Milky Way is here. So we have a telescope here. So then FRB comes from here to there. And that's fine, right? And then what we can measure is dispersion measure using FRB. And then dispersion measure is counting all of the plasma between telescope and FRB. This includes plasma in host galaxy. Host galaxy means the galaxy where FRB happens. Okay. In which FRB happens. This is people call host galaxy. Okay. Within this galaxy, there should be plasma here. Okay. This is included in observed dispersion measure. And then this intergalactic part. Intergalactic part I already explained, right? So this is intergalactic part. Also, plasma exists. And then Milky Way part. In our Milky Way galaxy, there should be plasma too. So therefore, roughly speaking, we can separate the observed dispersion measure into three different components here. DM host galaxy, DMH. DM IGM, so this is intergalactic medium. And then DM Milky Way components. Okay. Then, the point is, DM IGM, so this part is related to Hubble constant. Okay, this is because, if you remember, this DM can be used as a distance indicator. So if you have large amount of DM IGM, so then it means it's far away. If small DM IGM, it means nearby. Okay, so therefore this is kind of a distance indicator. That's why we can measure this distance part. Okay, distance part using dispersion measure. That's a kind of simplified explanation. So that's why people can explain the constraint Hubble constant using dispersion measure or fast Fourier burst. Okay, this is how it works. Okay, basically DM can be a distance indicator. Okay, that's one way to explain. Okay. Anyway, point is a cosmic average of DM IGM can be described by using Hubble constant, and there is an analytic solution to this DM average, DM IGM average. Okay, so there's an equation here, so we can calculate by hand. There's an analytic solution. So then this solution includes the Hubble constant here. So that means if we derive DM IGM observationally, we can measure Hubble constant. That's very simple. Okay, I forget. I ignore coefficient here, but the coefficient given by these difficult equations. But anyway, this is how it works. Then, that means this dm IgM is the most important regarding Hubble constant. And then we really want to derive this one. Then to do so, what we have to do is, there's a dm observation here. Observed dm, sorry. Then we need to subtract these two components, dm Milky Way and dm host galaxy. Okay, ma. And then dm Milky Way is fine. This is doable. Subtracting dm Milky Way is doable because there are many dispersion measures. There are many measurements of dispersion measure in our Milky Way using pulsars, not FRB, but there are many pulsars in our Milky Way galaxy. Using pulsar, people can also measure dispersion measure. So then we know that how this dm distributes in our Milky Way galaxy along different line of sight. They have a kind of good model of dm Milky Way. So this depends on which direction you are looking at in the universe. Okay. So then there are many pulsar observed pulsars in our Milky Way galaxy. So therefore, people already know that how much dm exists in our Milky Way. This is measured from pulsar. Or we can derive this using model. Model is optimized to explain the pulsar observation. Anyway, there's a model here. We can trust this, okay? We have kind of better understanding on this. But problem is this one, dm host. This is totally, we have no idea about this, almost. We don't know how much dm exists in host galaxy of FRBs. This is a source of significant systematic error. Okay, so you can imagine if we get wrong here, if we put the wrong number here, so then we are subtracting wrong number from dm orbs, then we get the wrong number of dm IgM, right? It's not good. And this is works as a systematic way. So if you overestimate DMH, then we underestimate dm IgM. If you underestimate DMH, then we overestimate dm IgM. So this is really systematics. Then we have to address systematics here because original problem is systematic difference, right? So the most important part is we really have to remove the systematic errors from the methods measuring Hubble constant. So this is the most important part because we want to resolve the systematic error here. But by default, FRB method includes possible systematics already here because we don't know much about the DM host. This has been a problem, so therefore people hesitate to use FRBs to constrain Hubble constants, okay? Because this includes a problem here. Then we don't know, there was no good solution to this. So therefore, what they can do was, for example, we just assume reasonable number. There are cosmological galaxy simulation, for example. Then they can estimate, right, from simulation, how much DM exists in host galaxy using theoretical simulations, for example. Then they have a kind of rough idea about rough number. Therefore, previous work, they just assume certain number, say 50. I don't mention unit, or 100. Or assume certain log normal distribution or something like that. But point is, anyway, so they needed to assume something here. And if you get the wrong assumption here, then you get the wrong answer here. So this is a problem. Therefore, we really want to address this source of systematics in FRB method. And John Chin is our student. I'm not showing here, I'm sorry. John Chin is my student. Johnson University, PhD student. And then he come up with a new idea. Actually, he come up with idea based on literature. Then he proposed to use scattering information to constrain DM host. But actually, this idea is already proposed by literature. And then he want to use this method to constrain Hubble constant. This part is new. Anyway, what is scattering? So let me explain scattering. There are multiple effects here. But scattering, okay. Let me check the time. Oh, I have time, okay. Let's say there's an observer here. And then a Hubble source here. And then this is a schematic diagram of plasma. Again, this is about the plasma, okay? Let's say this is the host galaxy here. And then inside the host galaxy, there are plasma here, okay? And then the simplest case is, okay, this Hubble source is emitting radio. And then this just go straight. And then come to observer. This is the simplest way, right? There's no effect, just go straight, that's fine. But there's another light path that can reach our telescope. This means this Hubble emission initially goes to different angle here. But scattered in plasma in host galaxy. Then change angle, they come to the telescope. Okay, man. This is also doable because this kind of scattering can happen if you have plasma. And then radio signal can be scattered like this. And then in this way, you can imagine there are two light passes here. Then the first one, this is straightforward. That means for given frequency, let's say, forget about the different frequencies. That's another story, right? Let's say for the same frequency, okay? Then we can forget about the dispersion measure. So time delay, the first one, time delay is happen between different frequencies, okay? Let's forget about it. For the same frequency, okay? If you consider same frequency, we can forget about time lag. For the same frequency, these two are the same frequency. Okay? A geometric distance is different, right? Speed of light is the same, but geometrical distance is different. Okay? Between this straight one and this scattered one. That means the distance in light path is different. So for given same velocity, I'm saying same velocity because same frequency. Okay? If you consider same frequency, the velocity is the same. For the same velocity, distance is different. So then again, this makes a time lag. Okay? I'm confusing you guys. We have two time lags about FRBs. The first one is dispersion measure. This happens between different frequencies. But if you look at the same frequency, still we see time lag. Because this light path takes longer light path, right? So therefore it takes longer time to arrive to the telescope. So therefore, we can see here, this is the light curve of FRB. Say y-axis is flux density, how bright it is, and as a function of time. So then the most of the emission arrives here, right? The bright here. But I can see some tail here. This is emission coming late. Okay. So you see this tail, right? Here. You see this tail. Okay. The shape of the light curve is asymmetric. Okay. You see tail here. So that means you have delayed component of FRB for the same frequency. Okay. For the same frequency. So there's a time lag here. This is delayed components. So this delayed component corresponds to this scattered light path because geometrical distance is longer. Okay, ma. So therefore, observationally, by looking at this scattering tail, we can measure how much plasma exists in host galaxy because this scattering becomes more significant. When you have more plasma here, you have a higher chance to get scattered. So therefore, by measuring how much scatter you have, then this can be, assuming some theory here, converted to the amount of plasma in host galaxy. So the point is, starting point is measurement. We don't need to assume certain number or value for DM host. So we can measure this degree of scatter here and then convert it to the DM host. So therefore, this is a kind of measuring DM host, not assuming. This is measuring DM host for individual cases of FRBs. And then using this measured DM host, then let's subtract it from DM observed. I mean here, here. I'm saying before people just needed to assume some number here, but now our method, Johnson's method, we can measure this DM host. Then let's subtract it. Then we don't need to assume it, okay, using scattering. Then we get updated DM, IgM, and DM and Hubble constants. This is a, say, idea about this. So therefore, by removing this assumption part, we hope we should be able to remove the systematics from this FRB method. Okay? Then this makes the FRB method useful for Hubble constants. That's what we expect, right? And then Johnson tested first using simulated data because for true universe, observed data, for example, we don't know true answer. So therefore, we cannot test how the performance of our method, right? Because we don't know true answer for observed data. So therefore, we made a simulated data first to check the performance of Johnson's method. Then he made a 100 mock FRB data. This is useful because when he generated mock data, we know everything about this mock data. True answer, we know. Okay. So therefore, we constructed the mock data first. Then for that, we know true answer. Then apply his method to this mock data. Then to try to get the answer. Then we can compare the answer from his method with true answer. Then to see if it's consistent or not. That's how it works, okay? That's the purpose of making simulated data here. We just want to make sure the performance of his method. And then, because this is simulated data again, we know the true answer here already. He prefers CMB. So she assumed the CMB Hubble constant. This is 68 or something like that. This is shown by vertical line here. X-axis is a value of Hubble constant. The y-axis is a probability density function. Anyway, the true answer of this mock data is here. It has to come here. And then let's look at the blue first. Blue is, we call it previous method, meaning that they assume certain value here, some reasonable value here. Okay, just assume. But what I'm saying is this can be the significant source of systematics. Then you get wrong answer. Then, yes, if you assume certain value here without knowing the true answer, then this is a probability density function of Hubble constant using previous methods. So if you assume something wrong value here and then you get a wrong Hubble constant. I'm saying wrong because true answer is here in this simulated mock data. And then this PDF is significantly deviated more than 1 sigma. 1 sigma is shown by vertical, this dashed line here. So therefore, this is statistically significantly deviated from true answer. So I can say that this previous method get wrong answer. Okay? Compared to that, if we look at orange, it is orange color. This is using Johnson's method. Johnson's method means he used scattering. He measures scattering and then to measure DM host and then subtract it. then he doesn't need to assume the M host. Then you may think this is a little away from true answer, but first of all, this is closer than previous methods. Okay, that's a good thing. And then another point is actually this 1 sigma range is shown by dashed line here again, vertical line. So that means within plus minus 1 sigma, actually Zhongqin's answer is consistent with the true answer within 1 sigma error. There's no statistically significant deviation here. So this is showing the performance of Zhongqin's method. So he can remove systematics, and then we hope he removed the systematics using the scattering method. And then remaining part is, say, statistical error. Remaining part is this statistical error. And in this case, his answer is consistent with what we assume true answer. Then statistical error is easy to handle because if we increase number of sample, then in principle we can reduce the statistical error in future. But anyway, so this figure is saying Zhongqin's method works at least better than this very simple assumption on DM host when we measure the Hubble constant. And then after making sure this point, then let's apply his method to the real observed data. Now this is about the true universe, okay? True universe. We don't know true answer, okay? But given this, we should be able to get true answer within 1 sigma, okay, error. Then let's use observed FRB samples. For his method, actually currently there are 30 FRB data sets that is available for his method. But maybe there are more samples right now at the moment, but at the time of publication or writing paper, 30 is the best effort, okay? Anyway, then result is this one. His PDF of Hubble constant is shown by black line here. And then we know the other studies, right? The local distance radar and the CMB. And the CMB is shown by yellow here. And then local distance radar is shown by blue here, right? Again, they are significantly deviate. They are not overlapping each other. This is the problem, right? And then, if we look at the Zhongqin's constraint, so this is, a peak is actually closer to local distance radar. We may support the type N supernova results, okay, using fast rate burst for this particular Zhongqin's paper. But it is also true that this CMA method is actually coming within 1 sigma of Zhongqin's method. So therefore, in this sense, actually, both of them are, Zhongqin's method is consistent with both of them within plus minus 1 sigma error. So that's maybe accurate way to explain this figure. Therefore, in this paper, we don't have conclusive answer which FRB will support local distance radar or CMB. So we don't know the conclusive answer. We don't have. But it's good to show this, our new method, then prove that this works. Then remaining part is actually not so difficult because now remaining part is just a statistical error. So currently the only 30 FRB sample is available, but in the future this number should increase. For example, if you really want to differentiate between local distance radar or CMB, which FRB supports, we need to reduce this statistical error smaller, right? And if we can reduce by factor 3, then this is currently 10% error, 10% statistical error. If you get a factor 3 reduction, then it will be 3%. If you get 3%, then this is small enough to differentiate between CMB and type I supernova. Then we will know the conclusive answer, which FRB will support. Then how to get this factor 3? And to get factor 3 in error, we need to achieve 10 times more sample. Or then currently 30. 10 times more sample means 300. Then how we get 300 FRB samples? This is, I would say, possible because now I'm switching to future. BURST is our FRB telescope in Taiwan. And this FRB telescope is supposed to find 100 FRBs per year. And then for most of them, we can find the host galaxy, then we can measure red shells. Then this is useful for Johnson's method. So therefore, 300 sounds like doable. If we just continue for 3 years using BURST, then we can achieve 300. Then that's not so far future actually. Therefore, the 3% statistical error using first read BURST and also using Johnson's method, okay, free of systematic error. This may really come in near future. So then we will know FRB supports whether CMB or type N supernova in near future. Therefore, I'm really expecting this kind of things. Then if I summarize, this is Johnson's part. This is not a summary of Holder talk. Sorry, it looks like Holder talk. FRB is interesting, exciting. This version measure can be the distance indicator or amount of plasma. So therefore, we can do the Hubble constant or baryon distribution in the universe. Anyway, this is related to cosmology. Okay, that's summary of scientific part. Then I'm going to future. As I mentioned, BURST will be very useful. So let me explain how useful they are. Then it comes to our project. So I think I finish in maybe 20 minutes or so. So this is our new FRB telescope project. Bustling Universe Radio Survey Telescope in Taiwan. So PI, leader of this project is Ueli Pen, Professor Ueli. He is in Taipei, Academia Sinica. So Tomo-san and I are collaborators. Okay, we are one of collaborators. Other people also get involved. Then this is very special. I don't really see similar type of radio telescopes. So let me go back to the introduction or parts. Then what do we want to do with this radio telescope? We want to observe FRBs, but what is the most specific major topic of BURST telescope? So this telescope is, I believe, very useful for understanding the origin of FRBs. That I really didn't mention this time, but this BURST project and the BURST telescope is useful for understanding origin of FRBs. Then we don't know what is origin, but if I select some of them, there are so many models for FRB progenitor or FRB mechanisms. So then I cannot list all of them, but there are scenarios that expect FRB emission from, say, white dwarf or neutron star binary, stellar mass black hole, magnetar or young versus supermassive black hole or supernebulons. There are so many candidates for the origin of FRBs. One of the promising objects is probably magnetar. I'll talk about this one later, sorry. Then, so far we don't know this one. We don't know origin of FRBs. This is mainly because the position of FRB is hard to find. You know, FRB is instant moment. So it's only 1 millisecond appear and then disappear within 1 millisecond. Within such short moments, it's hard to measure the distance, location of FR beads precisely. So therefore, current situation is, for many cases, not everything, but then for many cases, the current situation is they can detect FR beads using telescope, but when they detect FR bead, the position of FR bead on sky is uncertain. There's a large error bar, error circle on sky. We don't know where it comes from inside of this error circle. So there are so many objects inside the error circle. Then we don't know where it comes from. Okay, which galaxy or which source it is. So we really have to make this error circle small to accurately pinpoint the location of FR bead on sky. So this is again schematic diagram, but by making this error small, then if you achieve this as small as 1 arc-second level, then you can see that there's only one astrophysical source within this red circle. If you can achieve this situation, then we are almost 100% sure that FR bead comes from this star. Okay, we can directly identify the source of FR bead, or we call progenitor of FR bead. This is emitting FR bead in this example. This is just a schematic diagram. I just want to explain how it works, okay? So this is the source. So this is something what we want to do. Then doing so, to do so, we need accurate localization. Means we need the accurate small error circle here. Then we can do this fortunately because FR beads are happening in radio. Then in radio, there's already well-established technology here, right? Interferometric observation in radio on this VLBI, very long baseline interferometry, VLBI. So we can do this. When at the time of detection of FR bead, we can also do this interferometric observation. Then we can achieve this. Finding progenitor or finding host galaxy. Then I forgot to mention. Then blue one is problem. The red one is a solution that we can achieve using burst. Okay. Do I have time? Yes. I don't have time much. Another problem in previous observation was field of view of radio telescope was limited. So you know field of view, right? So field of view is kind of when you take a picture using your smartphone camera or telescope has always limited region that you take a picture at one time. If field of view is very small, like this on sky, FR bead they are happening over the sky. What if FR bead happened outside the field of view of telescope? Then basically we cannot detect light outside field of view. So therefore, using small field of view, we are missing significant amount of FR beads. So that's another problem in previous observations. So therefore, in our burst project, we try to make it as large as possible. This is nearly covering northern sky, nearly whole sky survey. So so burst project, our field of view is almost whole sky. So therefore, if it happens here, then we can find it. Okay. No missing population here. To do so, we have to forget about this traditional radio telescope. So this is good in sensitivity. They can collect many radio waves using this dish-like telescope, right? This is high sensitivity. But high sensitivity doesn't mean high wide field of view. So for this kind of traditional type of radio telescope has usually a narrow field of view on sky. This cannot achieve whole sky survey. Because this sensitivity has a pointing to a certain direction line on sky. But we want to cover all the angle on sky, all the angle. To do so, we can do cheap. what a difference. So in Taiwan, so we are making this fishbone like the antenna. So this antenna has sensitivity to many angle directions on sky. Okay, not only particular this direction. So this can have a sensitivity to different directions. Then this has an extremely wide field of view. Then we don't use only one. We use many of them. So we plan to put many radio antennas over the Taiwan and also over the country, other countries, international places. So then currently, so I think we finished deploying 256 radio antennas in Fusan. Fusan is Iran. I think Fusan is, there's a botanical garden over there. So then we are borrowing the place for this project. That place is really radio quiet place. Then background level is very small. So it's good for radio astronomy. This is the main station. So we deployed 256 antennas already. And then, as I mentioned before, we need to do VLBI observation. So this is combining multiple stations all together to make apparently single or large telescope. And then we have different stations over Taiwan. This is not all of them, I think. But anyway, one in Fugui, Nanto, Donsha is, I think we are just thinking still. Green Islands, I think people are deploying now. And then this is Taiwan's, and also Jinmenma. I think I have to update. But anyway, we are actually Taiwan has kind of wide area if you include islands actually. Then making long baseline. Anyway, sorry. So we are deploying these kind of things. Then again, let me emphasize in the good point of this radio telescope. This is a kind of radio instruments. We use this kind of very cheap one, but this is very good for our purpose. And this can achieve very wide field of view on sky. This is just a schematic diagram of field of view on sky. So far, this Canadian radio telescope, or CHIME, is the most, one of the most powerful instruments that can find FRBs. This is finding so many FRBs now. But actually, astronomy people didn't expect that FRB becomes so popular at the time of designing this telescope. So actually they wanted to use this telescope for multiple purposes. So therefore this radio telescope is not optimized to FRB only. So they want to use this for different multiple purposes. So therefore this is not optimized to FRB. So that's why we can overcome this great project using cheap antennas. Because again, CHIME's field of view is small, so this is not optimized for FRBs. This is small on sky. But we have even larger field of view. Say this is the size of the moon on sky, so our field of view is much, much larger than the size of the moon on sky. Anyway, by optimizing this design to FRBs, we can still overcome in terms of field of view. Okay, this is important. Another point is a survey volume or survey area. So now I have to remind you guys one of the it's not working. One of the possible scenario of FRB. This is a neutron star merger. If you may have heard about this, then this may emit a gravitational waveline. So therefore, depending on different scenarios, we may expect, say, a multi-messenger counterpart of FRBs. For this case, we may expect a gravitational wave happen at the same time as FRB. That means it's important to search for the same volume in the universe. But unfortunately, previous observations this is also a schematic diagram, simplified one. FRB telescopes are detecting FRBs within very narrow field of view at very distant universe. So therefore survey volume is like this, very sharp triangle here. This is what we are observing using current radio telescope. But the GW detector is survey volume is, survey area is, say if I simplify, that's the whole sky to the nearby universe. So this yellow and the magenta doesn't have a lot of overlap. So this may be the reason why we don't really see gravitational wave counterparts from FRBs, because this has very small chance to have simultaneous observations. We want to improve this. So therefore, by focusing on nearby universe using extremely large field of view, our burst project can maximize the overlapping survey area between FRB and multi-messenger counterparts. So if you really find it, then this will strongly constrain the origin of FRBs. Okay. Let me, I think this is important. Let me explain this too. This is showing the uniqueness of burst projects. So y-axis is a field of view of radio telescopes over the world. X-axis is sensitivity. I'm sorry, if you go left, sensitivity is good. So that means top left corner is the best telescope, okay? If you approach top left, it is the best telescope. CHIME telescope is located here. That's good, actually. It's here. That's good. But compared to this guy, our burst project has significantly larger field of view. So we are much better in terms of field of view. Okay. Then there is no other radio telescope competing this parameter space so far. I mean, at the time of this 2022. So then maybe these two projects, STEAR2 and GREX, they are American projects, has similar field of view in y-axis, but sensitivity is very different. Okay, so left is better. So we have several orders of magnitude better sensitivities than them. So therefore, we are very unique in this parameter space. That means our FRB sample will be also unique. SK2, this is a future world largest radio telescope, SKA, square kilometer array. Of course, they will detect FRBs too. They have a highest sensitivity because it's the largest radio telescope, highest sensitivity. But field of view is probably not as large as our burst telescope. So therefore, even after world largest telescope starts science operation, we can still keep our uniqueness using our FRB telescope. That's my expectation. So therefore, I expect Taiwan can really lead this FRB science in future using burst telescope. That's my expectation. I'm sorry, I don't have time. What do we expect? Let me quickly summarize. One thing is we really pinpoint the progenitor of FRBs. There's actually one successful case in the past. There was very bright FRB happened, and then FRB instrument detected. The error circle on sky is huge. They don't know where it is at the beginning. But by using CHIME and other fast telescope with another radio telescope in China, this is the currently largest radio telescope, they can pinpoint the location of FRB, this FRB, and then they found a magnetar in our Milky Way galaxy. So therefore, for this particular case, they really identified this FRB came from magnetar in our Milky Way galaxy. So I can imagine this is a kind of expensive observation because to do so, this is only one successful case to identify FRB progenitor. They use 3 cutting-edge radio telescopes all together to find this magnetar here. But they needed to use these 3 big radio telescopes. So that's expensive. But after burst starts science operation, I expect we can do the same thing using only single instrument, which is a burst. Because burst has a wide field of view and localization capability. So therefore, and also sensitivity to nearby universe. Before they needed to use multiple telescopes to do so. But we can do the same thing using only burst. Therefore, I hope we can increase this kind of successful case a lot in future. I think I ran out of time. So I think this is the most important point. So therefore, maybe I think it's time to stop speaking. So then maybe I think I take some questions about my lecture. Okay, so I'm sorry for taking too long time. So I finish here. So then thank you very much. So I take questions.
So it's time for Q&A session. Do you have any questions?
So when you were talking about the dispersion measurement of intergalactic medium, I wonder if you assume that all the intergalactic medium are homogeneous on the way that on the way of
that's a good question. Actually, that's from single measurement. Actually, we cannot know whether it is homogeneous along line of sight or not, because this dispersion measure is accumulated quantity. More specifically, this is Coulomb density of free electrons. So Coulomb density is this integrated over the along sight line. So we only know the integrated quantity along different line of sight. So therefore, in principle, from single measurements, so we don't know how this electron density is distributed along sides. But we know different line of sight, so we can see varieties.
Because I was thinking if this accuracy of dispersion measurement will affect the localization ability of which distance is the source.
That's a very good question. I believe so. Yes, I believe so. Because you may have fluctuation along sides. So then I think this fluctuation will affect the accuracy of distance measurements from the M. But we have a kind of idea how much this dispersion fluctuates. But this is different line of sight, but I think this is the same thing. So even for the single line of sight, there's an uncertainty here, right? So I think this is coming from fluctuation of density in the universe. So therefore, I think this expected uncertainty along single line of sight is, I think, estimated from this expected fluctuation along different line of sight. I think that's the same thing. So in that sense, that's a very good question. If you want to measure distance using dispersion measure, you need to consider this error size budget. Okay. So then usually this is, say, more than 10% or so. But for cosmological purpose, so important thing is this cosmic average. So this is there's an analytic solution. So therefore, we want to know the averaged value of this line. So therefore, individual data points just fluctuate, yes, a lot. But for cosmological purpose, we just want to measure accurately, that is average. Then it gives you the cosmological parameter. Does it answer to you? Oh, okay, thank you. Good. Very nice question.
Any more questions?
Oh.
Interesting about could you make this speaker maybe with the modify this problem by adding some slice linearity? Since this is a linear function.
You mean this line?
Yeah.
Looks linear.
So, does it make sense to add some non-linear model? So does it make sense?
I think so. That's also a very good question. If we assume lambda CDM model again, then there's an analytic solution to this cosmic average. And then this solution is actually not perfectly straight line here, actually. If I expand this one to even higher redshift, actually this line starts to deviate from straight line, actually. This is actually curved. This is curved, actually, theoretical prediction. But this is just a theoretical prediction line. So therefore, we can also derive this curve using many data points by adding more data points. And then we can try to fit curve to data points. And then to see if this curve is really matching to what we expect from theory. That I think really makes sense. I think that's very interesting. But just because currently we don't have not so many data points. Actually, we have more data points here, but probably that's still not sufficient to test this curvature of this line, probably. But future, I think we should be able to do so. I think that's very important.
Any more questions?
I have a question. So
Sure.
One subject that people are interested in are identifying the sources of FRBs, right? And I imagine there would be many different types of sources that would be possible. And I think it is reasonable to think that if some FRBs come from the same source, the same type of sources, then the signals would have similar characteristics, right? So, do we observe similarities between different FRBs that
That's
correspond to
sure. That's okay. That takes another 1 hour to explain. But that's a very, very good question. I think we have many answers. But one important thing is, I think so. The simplest characteristic is how many times the FRB happens. Say, for example, I didn't explain this, but then there are 2 different types of FRBs so far. The one is repeating FRBs. Say, in this schematic diagram, FRB is coming only 1 time, right? But this FRB source can emit multiple times FRBs. So therefore, multiple FRBs are actually coming from this FRB source many times. This is really confirmed for some cases. This we call repeating FRBs. Then there's another type. Somehow FRBs apparently happens only 1 time from this source. Then there's no FRB anymore. So then it happens only 1 time and it can repeat many times. These 2 are maybe different origins because naively speaking, 1 time burst may be related to explosions, for catastrophic events, say supernova explosion or something like that. Then repeating, this cannot be explosion. If projector really explode, then this cannot repeat many times. So in this sense, these 2 may be different origins. But I'm saying maybe. This is because observationally, finding repeater is fine. We are 100% sure they are repeating. This observationally confirmed. But single FRB, one time, this is hard to prove that this is truly single time because this may repeat the future or this may have repeated in the past, but we just didn't observe. This is hard to prove only one time or not. So this is coming from observational limitation. We cannot observe everything in the universe, right? There's always a limitation in observation. So therefore, proving this is difficult actually observationally. But naively, people may expect they are different. So then, that's one thing. Then if they are really different, repeater, non-repeater, then they may have different characteristics in radio. They may emit different signals in radio. That's what the people are trying to find. Then one thing is, yes, a non-repeater may be broad, non-repeaters only one time. They may be broad in spectrum. So this is a radio signal, right? So this has a spectrum. And then the range of spectrum of FRB is wider for non-repeater, tend to be wider. And the repeater is narrow in spectrum. But non-repeater is narrow in time. Narrow in time. Broad in spectrum, but narrow in time. And then repeater is narrow in spectrum, but broad in time. Broad in time means the light curve is broad. So therefore, they may show different characteristics. But because of this problem, we don't know if this is truly repeat or not. So therefore, because of this problem, so we don't know. So therefore, people are trying to understand now. But there may be difference actually, yes.
Thank you.
So any more questions? For online people, if you have any question, you are welcome to ask to speaker. So if there's no more questions, so let's take the Professor Hashimoto again.
Easy question.
Sure.
Very, very easy. I want to know if we use the data array, we can put the detector on the moon. Will it help to measure this FRB?
A moon?
Yes, at the moon.
Moon? I think, I mean, if we can really do that, then theoretically, I think moon is probably better place than the ground because FRB is really happening in 1 gigahertz in radio. The 1 gigahertz is, we are using a lot of smartphone. This 1 gigahertz, this is about 1 gigahertz, right? 1 to 1.7. So this is contaminated by our smartphone signal. So we are using a lot of radio in similar frequency. So then it's usually difficult to find radio quiet place in the ground because many people are using, right? So therefore, difficulty is we really have to go to rural area where there is no people. In that sense, probably on the moon is better because I may expect the radio background is much smaller than ground in the earth. Then probably it works better. But then, you know, it's always cost performance problem. I mean, theoretically probably better on the moon, but it takes more money. So then I don't know how difficult it is actually. But theoretically, I think it should be better on the moon. Good question.
So if there's no more question, let's thank Professor Hashimoto again.
Thank you.